Hello, my name is Mr. Wilke, and I'm here to teach you about the chi-square test for goodness of fit. So, we're going to learn some stuff. Hopefully everybody's having a nice time staying at home, working from home, living at home. Hopefully everything's not too crazy yet. Yes? Good? Okay. So, I'm still at work, but my classroom is very empty. So, once again, let's take a look. Desks empty, all empty. Follow me this way. Peter Murphy, signed by Peter Murphy and David J. Ha! Nice. All right. Anyway, let's learn some stuff. Chi-square test, goodness of fit. Are we ready? So let's say you want to check your calculators. Random number generator. Now, if things are random, anything can happen. That's true. But what happens over the long run when something's random? Yes. Yes, that's correct. Exactly. Over the long run, things that are random do have a pattern. So if I'm looking at all my digits on my random number generator, let's say 0 through 9, then what should happen? They should all show up about the same amount of time. What kind of distribution is that? That's right, a uniform distribution. Well done. Okay, so what I'm going to do, and you can play along with me. You should have your TI-84s. So get your TI-84s out if you haven't already. Hit pause if you need to. Grab your TI-84. What we're going to do is we're going to put 100 numbers We know how to do that. Let's go to our calculators. We're at our list screen. All right, if you don't know how to get to the list screen, hit Stat, Edit, and there it is. So I want 100 random integers from 0 through 9. So highlight list 1, hit Math. Go over to probability. Random integer is number 5. We're going to type in 0, 9, 100. That's 10. 100. There we go. Enter. And there it is. Now, do we have to look at these and say, well, there's 1, 5, and no, we don't want to do that. That's going to take too long. So we'll sort them. So let's hit Stat, Sort A, L1, Enter, Done, Stat, Edit, and all we have to do now is count how many of each do we have. So it looks like I have 12 zeros. Can you guys see this board well enough? I don't know. Anyway, what I'm doing is I'm writing down the number of each digit that I have. So 0, I have 12 ones. Looks like I have 14 ones. So what does this mean? This means I'm going to have less of something else, right? Because clearly I should have roughly 10 each. Now, does this mean my calculator's favoring the lower numbers? I don't know. Let's find out. 2s. I have 17 twos. That seems like a lot. I don't know. Let's find out. Threes. 1, 2, 3, 4, 7, 6 threes. Now, if you want to check to make sure you've counted correctly, this is our 49th number. If I take 12 plus 14 plus 17 plus 6, I should get 49. Do I? There's 20, 32, 49. Hang on for the announcement.
Attention faculty, there are some pastries and coffee in student services conference room, so please help yourself. Again, there are pastries and coffee in student services conference room. Please help yourself.
We're going to take a quick break so I can go get some pastries and coffee. No, I'm just kidding. All right, let's get through this because there's pastries and coffee. Where are we at? 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. 8 fours. All right, so the first 5 digits, I have 56. It should be right around 50. 56 isn't that bad. We'll see. Let's see what it looks like. So 5, 2, 3, 4, 5. 4 5s. Interesting. 6s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 6s. 7s, we've got 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. 11 7s. 8s. 6, 7, 8, 7. And there's 10 numbers left. All of them must be 9s, so there's 10 9s. Perfect. Okay, now, does this seem like it's working? Roughly, they should all be 10. Now, should we do a 2-prop z-test to show that 2 is different from 5? 2 shows up 17% of the time, 5 shows up 4% of the time. Should we do that? No, definitely not, right? We don't want to do that. Instead of testing each thing, we're going to do one test to see if the observed distribution is different from the hypothesized distribution. Okay, so we call this the chi-square test. For goodness of fit. Now, you'll notice it's chi-square, not chi-squared. It's just one of those things. Chi-square. We'll notice it's pronounced chi, not chi. If it were a chi test, it'd be a t-test. All right. Chi-square test for goodness of fit. Okay, so we're going to calculate the chi-square statistic by finding the sum of the observed minus expected counts squared over the expected. Okay, so what were the expected counts for each one? 10, good, that's right. Each of these should have shown up 10 times. The observed, we got 0 12 times, 1 14 times, 2 17 times, and so on. So your results probably different than mine. If they're not different from mine, then I wonder if their calculators really are generating random numbers. Okay, so let's go back to our calculator. And in my list 2, I'm going to put my observed counts, which are 12, 14, 17, 6, 8, 4, 11, 11, 7, and 10. What are my expected counts? A whole bunch of 10s, that's right. So 10, that's a 1. 10, 10, 10, 10. Be sure to follow along with me on your calculator. And one more 10. There we go. All right, so if I want to calculate the observed minus expected squared over expected, what I can do, come over here, observed is L2, expected L3, observed, expected. So in our L4, let's do parentheses, L2 minus L3, parentheses, squared, divided by what? Observed squared, observed minus expected squared over expected, so divided by L3. And there we go. Now, let's add all these up. How do we do that? We could run one variable stats, that'll work, sure. Run one variable stats on L4. And the sum is right there, 13.6. So that's our chi-square statistic. The sum of observed minus expected squared over expected is 13.6. Okay, great. So what does that mean? Wonderful question. Let's find out. So our chi-square statistic, we said was 13.6. Now, let's talk about the chi-square distribution. Chi-square distribution is always positive, it's always skewed right. Okay? Does that make sense? Think about why. Why is it always positive? Well, observed minus expected square over expected, we're adding them all up. It makes sense that that's always positive, right? Good. Okay, why is it always skewed right? Well, what's the most likely thing to happen? It seems like the most likely thing to happen should be the expected, but it should actually be more a little bit off, right? So chi-square is going to depend on, what do you think? That's right, degrees of freedom. So, how are we going to find degrees of freedom? Anyone want to guess? Yeah, of course, as always. Now, here's the real question. How many is ours going to have? Is it going to have 99 degrees of freedom, or is it going to have 9 degrees of freedom? What's n going to be? N is going to be the different categories, right? So we had 10 different categories, so that's 10 minus 1 is 9 degrees of freedom. 100 was the counts. The counts isn't what matter, it's the categories. So we've got n minus 1, we've got 9 degrees of freedom. So here's our chi-squares. If does this make sense? If df equals 1, so that's like heads or tails, you're most likely to get the same, but you know, could be a little bit different based on you know, if I have 100, I'm more likely to get 50-50, but the chi-square statistic would be the same with 49 heads, 51 tails versus 51 heads, 49 tails, right? So it goes up a little bit, comes back down. There we go. Okay, so with 4 degrees of freedom, with 8. What's it starting to look more like? It's starting to look a little more normal. Now, will it ever look normal? No, because it's always positive and always skewed right. It's never going to quite be normal, but it's going to start looking a little bit more normal the further we go out. Okay, so let's talk about our goodness of fit test. You can abbreviate it GOF for goodness of fit. That's what your TI-84 has. If you have a TI-83, it does not have the goodness of fit test on it. The 84 does. So that's the only reason to buy the 84 is just to get the goodness of fit test. I don't know if that's true. Okay. Texas Instruments should give you money for that, right? Yes, good. Thanks. Thanks, guys. All right, goodness of fit test. Determine whether the population has the hypothesized distribution. So what's H not going to be? Okay, so actual population proportions equals the hypothesized. Conditions. All expected counts are greater than 1. No more than 20% or less than 5, and as always, randomize when you can. Okay? All right, so so the chi-square distribution can be found on a chi-square chart, which is in the back of your book. It will be attached to your test. It will be attached to the AP test. Hopefully we're still taking AP testing this year. We'll see. All right, chi-square distribution, back of your book, or you can use a chi-square CDF, which is lower bound, upper bound, degrees of freedom. Okay, so we found our chi-square was 13.6 with 9 degrees of freedom. So just looking at the calculator, let's hit second vars, which is the distribution menu. There it is, chi-square PDF. So CDF should be number 8. There it is. Chi-square CDF, we said 13.6. Now, this is a weird one with infinity here, so just do a ridiculously big number. I've seen some people do this. That's ridiculously big, okay? It's all that times 10 to the 30th, huge. I've seen people do like 10 to the 99th, whatever. And degrees of freedom is 9, and there's our p-value. What's our p-value? 0.1372, what does that mean? Well, it's higher than 0.05, so if we're using an alpha level of 0.05, we would do what? Reject or fail to reject? Fail to reject is correct. Good. We're going to fail to reject H naught. So this will tell us there's not enough evidence to show that our calculator, random number generator, is not working. So do you want to see formalized inference? If you do, keep watching. Let's do this. If you think you already know it, watch it anyway. Step 1. What do we want to know? We want to know So we want to know if our calculator is random number generator is basically putting out a uniform distribution, okay? Now, this is something to be aware of. H naught, we can say, I could say that what? That, right? Or I could say hypothesize equals observed. The reason I prefer this one, for HA, we're not going to say P naught is not equal to P1 is not equal to P2, because some of them could be equal, but one of them is different, and that's enough. So we have to just say at least one proportion is different. Step 2, conditions, as always, right? Random, all greater than 1, no more than 20% less than 5. Are we good with that? Were the numbers picked at random? Well, it's a random number generator, so now, sometimes the random thing doesn't necessarily matter. This case, I mean, it was a random number generator. You try to, if it's something that should be random, randomize. If it's something like this, it doesn't even matter. Okay? They're going to have a homework assignment where you get a bag of M&Ms and see if the colors match up to what they're supposed to be. I mean, you're going to pick a bag of M&Ms and look at your bag. Okay, you're not going to say, all right, let's pick a random number out of the phone book. Say, here, you're a store, good. Do you sell M&Ms? Good. Let's buy one. Give me the spin a spinner, eat the bag. We don't do that, okay? Just go buy a bag if you can. I don't even know if we can get to stores yet. Okay, our numbers are picked at random. Sorted, yeah. All expected counts. Now, when it says no more than 20% or less than 5, so we have 10, which means we could have 2 of them with expected counts of 4. Now, since it's supposed to be uniform, they're all 10, it's fine. But, I mean, let's say it was something with different proportions, you know, if we're rolling dice, 2 dice, okay? If we're seeing, 2 and 12 show up less than 7, so those could be less than 5, would be all right. But here, it's all the same. Now, all of ours are greater than 5. Can we just mix that in with the first one? Probably. Sometimes I'll say all counts are greater than 1 and 5, and just show that, hey, look, I know this one. Hey, look, I know this one as well. Okay? We proceed. Chi-square test. For goodness. No fit. Step 3, math. Step 3 is where we do our inference. So to show your work, what I want you to do, it's the sum, right, of you don't have to write this. This is what's on your formula sheet, except they write out observed and expected. So what you're going to do, so you're going to write chi-square equals. Now, my first was that one. My last was that. So do your first plus dot 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 plus, do your last equals 13.6. What else do we need? P-value, good. P-value was 0.13728, or we'll just call it 1373. We also need degrees of freedom was 9. That's correct. Good. Okay. That's it for step 3. Step 4. Step 4. Since our p-value was that is greater than alpha equals 0.05, we reject or fail to reject? We fail to reject. H naught in favor of HA. There is not enough evidence to show our calculators random numbers are different than expected. And that's it. Any questions? Any questions? Well, since nobody's here, you can't really ask questions. If this goes up on YouTube like the plan, you can comment questions and I'll answer them. Please comment just about this, not about my tattoos. I know I have them. I'm just assuming this is going viral. Everybody's going to watch it because, wow, look at this. I learned the chi-square goodness fit test from this guy. It won't go viral. There's going to be like 6 people that see this out of a class of 105. But that's okay. For those 6 of you that watched, well done. Anyway, your assignment is 13.9 to 13.12. One of these requires M&Ms. If you don't want to do the M&M problem, and I don't remember which one it is, that'll be up on your canvas. All is good. All right, any questions? No? I hope that helps. See you guys soon.